Hello, everyone. Welcome to the 14th webinar in the Joint Transit webinar series, which will cover different projects related to advancements in pedestrian and bicycle safety from three quite different perspectives. So today we are privileged to have 4 transportation experts presenting in this webinar. We will have 3 15 to 20-minute presentations. First, we will have Dr. Nick Ferenchak presenting autonomous vehicle communication strategies modeled in virtual reality. After that, we will have Dr. Lee and Dr. Sirisha discussing the use of Lidar sensing technology in capturing pedestrian behaviors at signalized intersections. And finally, we will have Dr. Feng presenting a naturalistic cycling study in Michigan. We will save the questions until the end of the 3 presentations for 15 group Q&A. So throughout the presentation, feel free to type any question in the chat box. Without further ado, I will introduce our first speaker, Dr. Ferenchak. So Dr. Ferenchak is focused on developing sustainable and resilient transportation systems, primarily through improved health and safety outcomes. His current research focuses on multimodal aspects of emerging transportation technologies and their impact on health and safety. Dr. Ferenchak teaches highway and traffic engineering on the undergraduate and graduate level. He is active in domestic and international societies, including the Transportation Research Board and Institute of Transportation Engineers. So Dr. Ferenchak, I will turn it over to you now. So feel free to unmute yourself and share your screen.
Great, thank you, Dr. Musa. And welcome everybody. Can everybody see my presentation there?
Yeah, we can see your presentation and we can see your slides.
Okay, great. So good afternoon, everybody. Thanks for being here. And again, thank you to Tran-SET for organizing this. And this is actually a Tran-SET project. So thank you, Tran-SET, for the support as well. So what we're doing with this project is we're trying to understand how to best have autonomous vehicles communicate with human users of the roadway. And with this presentation, we'll really be specifically focusing on pedestrians. We're just an hour ago, I wrapped up data collection on bicyclists and human drivers as well. We haven't crunched the numbers yet. So we'll be focusing on pedestrians here, but we'll also just mention some of the findings that we're seeing for bicyclists and drivers as well. So the idea here is that right now there's a lot of communication going on our streets. If you're walking or biking, you might make eye contact with a driver. They might wave or flash their lights. There's a lot of communication going on, but in the future, if we have autonomous vehicles on the streets, there won't be any humans in those cars, at least some of the time, or they won't be paying attention to what's going on the street. So how will we know, has that AV seen me? Is that AV going to let me go? So we're looking at different strategies for communication to improve that understanding. The big picture here is that we're told that AVs are going to be on our streets in the future, but public acceptance is still pretty low. So there's a bunch of surveys that have been run, and generally it's about 50-50, maybe 50% of people say, I don't want to see AVs on our streets. 50% say, yeah, sure, I'd like to see AVs. Research has shown that by providing communication from these new technologies to human users of the roadway, we can improve that acceptance. So if we want to get all of the benefits that AVs might be able to provide, we need to make sure that AVs are appropriately rolled out and implemented onto our streets. So communication and acceptance of this new technologies is important. To do that, we're really looking for one simple uniform language. So think about brake lights or turn signals. No matter where you are in the world, within a split second of seeing one of those lights, you know what that vehicle is doing. So we'll see in a minute or two, auto manufacturers have been throwing out all kinds of different ideas for communication interfaces and different strategies. We're trying to figure out which of those strategies is most effective to develop one uniform language. Really where we want to go with this is, again, like I said, hopefully this will improve perceptions So we'll be talking about things like understanding, comfort, trust of these new technologies, and then really at the end of the day, does this improve people's acceptance of these new technologies? The bottom right picture, this research is also important for safety reasons. Obviously, if you're a pedestrian or bicyclist using the roadway and there's an AV coming up and you don't know, has that AV seen me? Is it going to let me go? There's obvious safety implications there. So better communication will hopefully improve safety. And then bottom left picture there, this will, we're anticipating, and we've been measuring this with the latest batch of data collection. We haven't crunched these numbers yet, but we are seeing that the communication is impacting behavior, so specifically perception reaction time when you're dealing with an autonomous vehicle. So if we're assuming a 1.5 second perception reaction time today with human drivers, maybe it takes an extra second or two once we have these new technologies on the streets. So that could have a really big impact on the microsimulation and the operations of our roadway environments. Specifically for this work, we're going to be looking at perceptions, and here are the main perceptions that we're looking at. So understanding, do you understand what the AV is intending to do? Comfort, are you comfortable interacting with the AV? Do you trust the AV? And then are you accepting of this new technology? And really this is in order from kind of the most influential to the least influential. You'll see when we get to our results that the interfaces really do impact understanding and also comfort. Trust is a little bit more difficult to impact, and then acceptance is probably the most difficult, has the least response to these different communication interfaces. So this is what the virtual reality lab looks like. Again, instead of buying an autonomous vehicle and putting people on the streets at risk, we're modeling all this up in virtual reality. So just finished this lab, the construction of this like 2 days ago. This area, we've got all of our equipment there in this picture, but this is usually a big open space for pedestrians, so you can put the headset on and just walk freely around the environment. And then we also have a bicycle simulator. Just got this one up and running a couple months ago. I think we might be one of the first in the country to have a fully immersive VR bike simulator. So there's a little sensor on the rear tire. As you pedal, the sensor detects how quickly the bike is moving, and you move in VR. When you brake, tire stops spinning, you stop in VR. And we also have a controller on the handlebars, so you can actually steer. So it's fully immersive, three-dimensional, realistic. You're not just sitting on a track in the VR environment. You can go wherever you'd like. Same thing with our driving simulator. So brake pedals, gas pedal, steering wheel, fully immersive, drive wherever you want in the environment. Again, like I said, the bicycle driving simulators, we just got that up and running, and we just collected all of our data. So I don't have data analysis on that yet, but I will share some preliminary results. But most of the results we're going to be talking about today are from the pedestrian experiments. So we brought 47 participants in for the pedestrian experiment. You can see this is pre-COVID, nobody's wearing masks. And we've continued this through COVID once we were allowed to. So this was a within subject experimental design. So each participant sees each of the interfaces. We'll talk about the interfaces in a minute here. That would bias people as they get used to interacting with these autonomous vehicles. It's a 15:8 VR area, and we have a wireless headset, so you can put on the headset and just completely be fully immersed, walk around wherever you want to in this environment. This is what the environment actually looks like. So we use HTC Vive headset and Unreal Engine 4, and it's a task-based experiment. So we have people hit this first button after they've kind of become acclimated with the pedestrian environment. And then a second button appears in the middle of the street, and they're tasked with, you have to go hit that second button. but there's an autonomous vehicle that is approaching. And that autonomous vehicle has on different interfaces. For this video, I showed all of the interfaces, but, oh, sorry. But for a typical trial, the autonomous vehicle only has one interface on at a time. Also, the autonomous vehicle sometimes stops for the pedestrian and it sometimes does not. So the participant always has to be paying attention, looking at the interface, figuring out, has this seen me? Is it going to let me go, or is it not? As far as the interfaces, we modeled, I think, 4 different interfaces here. And we base this off of vehicle manufacturers, the ideas that they're throwing out right now. So the top left, you can see there's a text interface on the grille, smart car, Google. Top right, there's a text interface either on the windshield or on the roof. It's Nissan and Smart AI. Ford and Volvo just have simple LED strips. That's bottom right. And then I think this one was Uber, and they have arrows here on the side mirrors. This one's my favorite one. We didn't model this, but this is Jaguar Land Rover. Their AV actually has googly eyes to look at you to let you know, hey, I see you, I'm going to let you go. So one of the more interesting ideas that's being thrown out right now. This is what our interfaces that we model look like. So that interface on the grille says, please proceed to cross, and the arrows blink. The text on the roof, it says proceed to cross, and the text blinks on and off. The LED strip, the LEDs kind of go in and out and then blink, in and out, blink. And the arrows on the mirrors blink on and off. For the pedestrian simulation, the pedestrians were up against the curb and they were able to see the front of the vehicle pretty clearly. Once we started getting into the bicycle and driving simulators, the bike and vehicles were further back, so you really couldn't see the front of the vehicle very well. So we actually added a 5th display, which is on the side door. But we didn't model that for the pedestrians. Okay, so on to our results. The first question we wanted to look at was, do these different interfaces improve perceptions? We're not looking at which interface is best, just having an interface, does that improve perceptions? And the answer is yes. So you can see here in these 3 columns to the left, with an external human-machine interface, you can see that our total number, and these were on a Likert scale, so higher numbers are better perceptions, more comfort, more trust, more acceptance, so on and so forth. So you can see 3.84 with the interface, 3.36 without. So there were significant improvement in perceptions when we added the interface. Of note, the smallest response was for question 7, which was acceptance. So you can see here, going from without an interface to with an interface, there's only a small change, 3.3 to 3.4. These other perceptions had much larger increases. So that's kind of a theme we saw throughout this research, was that acceptance is much more difficult to shift than understanding or comfort or trust. Also of note, females in general reported higher scores and better perceptions. You can see here without an interface, females had much larger, much higher scores, but males had a much higher response to the introduction of an interface. So you can see male responses went from 3.1 up to 3.9, so much larger response, whereas females in general had higher responses, but there wasn't a big response to the introduction of the interface. As to which interface was or had the best perceptions, the 2 text interfaces had significantly higher scores than the other interfaces. And the text on the grille was the highest for just about every single category that we measured. One thing of note is, again, acceptance was an outlier. So just about every other perception that we measured, text grille was highest, 4.66, text roof was second, the side arrows was third, and then LED windshield was the poorest perceptions. For acceptance, it was actually the LED windshield, 3.76, that had higher perceptions than any of the other interfaces. So again, acceptance is kind of this outlier here, had different patterns than the other interfaces. So in conclusion, we're seeing that yes, the introduction of an interface does definitely improve people's perceptions of AVs. Females generally reported higher scores, but males had a larger response to the introduction of the interface. The text interfaces got higher responses than the non-textual interfaces. The text on the grille had the highest response for every perception other than acceptance. And so acceptance was kind of this outlier. There was not a big response to the introduction of the interface, and had the best responses with the LED windshield. So it's a bit of an outlier there. Some other preliminary conclusions that I'm just adding in here. We haven't crunched the data on this quite yet, but just from what we're seeing by bringing people into the lab, the drivers, again, really prefer this side interface. So when you're at a four-way stop, you're back a bit further, you really can't see what's going on the front of the vehicle. They're really preferring this interface on the side. I think we only found one piece of research that was really looking at these types of side interfaces. Almost all the conversation going on right now is the interfaces on the front. So we think this is going to be an important part of the story. Pedestrians, as you can see, front of the vehicle, at least if the vehicle is on your side of the street, that seems to be adequate. Bicyclists was a little bit in between. So bicyclists were a little bit further back. So they liked the side interface, but not quite as much as the drivers. With the data collection that we just completed, we are actually bringing people back longitudinally over time and testing them to see whether there's a learning response to these new interfaces. And we're finding that yes, there definitely is a learning response, and it takes place pretty quickly. So after just a couple trials, people start to get the hang of, oh, I know what this interface is telling me. So there definitely is a learning response. We were expecting that we saw that the text interfaces are a bit more complicated, but they're preferred when people first interact with autonomous vehicles. We were expecting that as people get acclimated to the technology, they might start to prefer the simpler interfaces like the LED strip. That's turning out to be true. The differences between the interfaces is definitely narrowing, but the LED interface has not with our testing over, we usually do 2 days of testing, about 20 trials for each participant. Over that time, the interfaces level off a bit, but the LED strip has not overtaken those text interfaces yet. The text interfaces are still preferred. So just some conclusions here and future research. Text displays are preferred, but there's obvious issues with that. Legibility, it takes a few seconds to read and perceive what the text is saying. There's language barriers. So how are we going to deal with that moving forward? What role does the size of the interface play on perceptions? So the text interfaces were just larger than the other interfaces. So is that what's causing people to like them more, or is it actually the text itself? So we want to look into that a bit more. The learning curve question, we already talked about that. We have some preliminary results on that. And yes, there definitely is some acclimation and learning effect there, but text is still preferred even after some learning takes place. What role might color sequence, time of day, weather conditions play? So there's a million different factors that we still need to explore. This is a very basic experiment up to this point. And then one thing I think is definitely something we want to do with our next steps is looking at multiple vehicles. So when there's 10 vehicles at an intersection, is text still going to work? Or do we really need to simplify these interfaces once we have very complex roadway environments being modeled? So thank you all for your attention. I guess we'll take questions at the end.
Okay, perfect. Thank you very much, Dr. Ferenchak. That was very interesting. So now I will introduce the speakers of our second presentation, Dr. Lee and Dr. Sirisha. Dr. Lee has 19 years of working experience in traffic engineering and ITS. He has a mixture of applied and theoretical expertise. In recent years, Dr. Lee and his research group focus on exploring the potential of new sensing technologies, traffic big data, and transportation management. Dr. Lee has been active in embedded system development for transportation management. He designed and developed the several travel time estimation systems based on Bluetooth, Wi-Fi, MAC address capturing. We have also Dr. Sirisha Kothori. She is a senior research associate in the Department of Civil and Environmental Engineering at Portland State University. Her primary research interests are in the areas of multimodal traffic operations, bicycle and pedestrian counting and safety. She is a co-chair of the research subcommittee of the Transportation Research Board's Pedestrian Committee and the Bicycle and Pedestrian Data Subcommittee, and the chair of the Multimodal Subcommittee of Traffic Signal System Committees. So Dr. Lee and Dr. Sirisha, the floor is yours now.
Can you see the screen?
Yeah, we can see your presentation. We can.
Okay. Okay, thanks, Mausa. Good afternoon, everyone. And my name is Taylor Lee. And today I'm gonna jointly present this our ongoing research with Sirisha. And Sirisha, you want to? I'm an assistant professor at the University of Texas at Arlington, and a PI for this project. Sirisha, do you want to introduce yourself and Nisi?
Sure. Good afternoon, everyone. My name is Sirisha Kothori, and I am a senior researcher in civil engineering at Portland State University and one of the co-PIs on this project. This project is funded by NITSI, which is one of the 7 national university transportation centers that's housed at Portland State University. And the other members of the consortium include the University of Utah and University of Texas at Arlington and a few others as well. In Taylor,
okay.
Please go ahead. Yeah.
Yeah, here's the outline of today's presentation. So first, we're going to introduce the importance of our projects and the goals of this project. After that, Sirisha will give a literature and technology review for pedestrian tracking and sensing technologies. Then I will go explain the LiDAR solutions we developed, and then Sirisha will present some field data collection and some preliminary findings. And following that, I will give a demo, then explain the future work. So we started this idea about two years ago, because in fact, 3 of PI co-PIs, we happen to working on pedestrian safety in different ways. So we realized, in fact, according to the NHTSA's report, in fact, our pedestrian fatalities reached the highest in 30 years. That means, well, we are driving technologies make us drive safer and safer. In fact, but if we walk on the street, we are getting more and more dangerous. So this is terrifying, because each fatality, pedestrian fatalities are going to be resulting in huge social economic losses. It means broken hearts and sheltered family. And also it means it lacks the transportation equity, because the transportation equity means the safety for everyone. So there's many ways to address the pedestrian safety improvement. We can have some policies, we have some law enforcement, but today we're going to focus on a technical perspective. In our opinion, we think we have 4 steps we can for improve the pedestrian safety. The first is we have to collect more pedestrian behavior data in the fact, because right now most of the literature on this topic is very old. In fact, believe it or not, when I'm going to teach in after 3:30, the literature I use for pedestrian behavior was published in 1984. So my student asked me why it is so old. I have no answer, because we don't really have a lot of literature. So once we have more data, we're gonna have a better understanding what's the current generation of people, their behaviors, and when they try to cross intersection. So that's enable us to revisit the guidelines for pedestrian facilities. For instance, do we for the walk time and pedestrian crossing speed, is that it should be changed or not? That's really about the observability of the system. So the first two steps is the focus of this project. After that, we're gonna focus on more trying to provide control measures to completely separate the vehicles from pedestrians, then even integrated with other physical system like a supplemental street light and the flash road start, etc. So let me turn over to Sureisha to explain the later in the technology review.
Thanks, sir. So one of the first things that we looked at in this project is to go back and look at the literature to see how pedestrians are detected at intersections and what their behavior characteristics are like. Next slide, please. Okay, so one of the first things that we looked at was perception reaction time. And as Nick mentioned earlier in this presentation, this is really important, and having values that are old or out of date has serious implications on the operations and the safety at intersections. And so the perception reaction time is really important for human factors research, for signal timing and crash reconstruction studies. And the literature and what we found was the average time used was 1 second. However, as Taylor also mentioned, this literature is old and out of date. And so in general, there is a lack of data that is being collected in the field, which would allow us to update these observations. So we found one study that was done over 20 years ago at 6 intersections in Los Angeles. And they found that while most pedestrians began crossing within 1 second of the walk indication, these values changed significantly when pedestrians were observed to look at the light, so then the values were lower, or they were significantly higher when they were distracted. And knowing what we know right now about how everyone seems to be just looking at their mobile devices at intersections, we expect that these values are quite high now. And so there is definitely a need to update this and collect more data in the field. Okay, so another important performance measure is pedestrian delay. And typically delay is one of the measures that is used to quantify the operation, the level of service at intersections, and is also used for intersection mobility. So many studies have focused on how to estimate vehicular delay, and the objective of signal timing right now is to reduce delay for vehicles and reduce their stops. But we've not, as a field, focused on pedestrian delay very much. And we know that pedestrians become impatient and they take risky behaviors when delays are greater than 30 to 50 seconds. And alternately, they are likely to show high degrees of compliance when delays are less than 10 seconds. We do have some technologies right now with the ATSPMs, the Automated Traffic Signal Performance Measures, and the use of high resolution data to collect pedestrian delay, but these are not yet widely adopted. Delay can also be estimated using some modeling techniques, but in general, it's not been either widely collected or modeled or used for decision making. Okay, and then finally, how do we detect pedestrians at intersections? And this has been accomplished through the use of push buttons, which have been operational since 1930s. And these are effective when they're working, but it's old technology. And a number of times when a pedestrian walks up to the intersection or to the crosswalk and tries to push the button, they get no feedback that whether the button is still working, whether the signal controller has taken or registered the walk call, and things. So oftentimes we see many pedestrians just banging on the push buttons, trying to make sure that their demand for service is registered. So the design is old and definitely has not changed much since the development of the accessible pedestrian signals, which offer a way to provide some auditory messages and tactile feedback to people with impairments. Research has shown that most pedestrians do not use the push button, but if you install the push buttons with visible and audible cues, then you do see an increased percent of pedestrians who push the button and wait for the walk sign. So that's basically increasing compliance. The other issue with the pedestrian detection system with push buttons is that they provide fixed walk time and clearance intervals. And so if you have slower pedestrians, older people who tend to walk slower than the normal population, then they might get stuck in the crosswalk when the indication changes, and that can become a safety issue. Next slide, please. So there's a growing recognition that detection needs to be passive, and whatever improvements we make need to be built into the transportation system. And we should not require anything more from the part of the pedestrian other than compliant behavior. So the thinking is that vehicles are detected automatically. They don't have to do anything other than just, arrive at the intersection and then they get served. So why do we require this for pedestrians? Yes. So we have, there have been some tests conducted both in the US and UK to look at these automated pedestrian detection systems. And the US trials involve the infrared and the microwave systems. And those results reveal that using these passive detection systems, pedestrians were less likely to begin crossing during the clearance phase, but the detection zones needed fine tuning because there were a number of instances of false calls and missed calls. Similarly, an experiment was conducted in the UK with Puffin Crossings, and these had the additional feature that they would dynamically extend the walk phase when the sensors detected that the pedestrians were still present in the crosswalk at the end of the walk indication. And so, which definitely is great for safety, but they also had issues with the sensors itself and with the accuracy of the sensors. And with the advances in technology, we've had a number of different types of sensors that are being used and being tested at intersections. And primary among them are the Lidar, video, and radar sensors. The radar sensors are not really applicable for tracking pedestrians because they have to be placed away from the intersection, and pedestrians at signalized intersections tend to cross there. The video sensors have some known issues with detection during low light conditions and adverse weather conditions. And so the objective of our study in this was to test the Lidar sensors, and these have the added benefit of being able to interface with the autonomous and connected vehicle world. So turn it back to Taylor, who will talk about the Lidar sensor system setup.
Yeah, thank you, Sureisha. So Lidar sensor, now let me explain what our developed Lidar sensor-based pedestrian safety solution. So first thing first, so what is a Lidar? Lidar is, in fact, is a device, also a method for measuring distance by illuminating the target with a laser light and measuring the time the reflection of light takes to return the sensors. So in the market, we have two types of Lidar sensors. One is mechanical 3D degree, like something we see a lot in the AV prototypes. So we also have another type LiDAR sensor called quality state sensor. That's directional. We have a multiple product in the market. So eventually, and also it is also being used for vehicles. So for instance, this is going to be a front LiDAR, but eventually the LiDAR will be smaller and hidden within the grille, so they can use to detect a collision use for the front collision avoidance, things like that. Okay, so in general, for a LiDAR sensors, we have a 3 levels algorithm. The first level is hardware level. That means how to make the LiDAR sensor generate a raw point cloud data reliably. That's a manufacturer's issue. The second, perception and classification algorithm, meaning that's one way the LiDAR sensor collect all the rebounded upon clouds. They need to cluster identify objects. So that's called the perception software. So right now it can be either provided by the hardware company, or they can provide through the third party. The third algorithm is more is domain specific applications. So this is our major development. So how to use those general perception and the object classification to build a scenario, build a case for our operations, traffic operations. That's our focus. So we integrate the LiDAR tracking algorithm, general LiDAR tracking algorithm within the real-time traffic signal controller at intersection to study the pedestrian behaviors. So there's a new trend for LiDAR sensors. Now we have more and more manufacturers come into the market. In general, it's still very expensive because now the automated vehicle industry is just a high demand for LiDAR sensors. And the market is being diverse. So other than the automated vehicle, they also go to the smart infrastructure, intelligent intersection, or even toxic gas monitoring. And also LiDAR manufacturers also open their perception software for new applications. That's open a avenue for multimodal smart city applications. So in fact, we were asked a lot about what's the difference between the computer vision solutions. So regarding the clustering algorithm, they are very similar. So they need to use a clustering algorithm, machine learning, etc. But LiDAR sensor is commonly considered more robust because it's intended initially for the automated vehicle to detect the surrounding object. So they must have a higher requirement than the infrastructure, especially in the extreme weathers, like a foggy storm and no storm and dark. So see on the left side is really intersection video in the dark night. In fact, I don't know if you can see, I was told by a presenter, see there's a pedestrian walking on the street. So they had a near misses with the vehicles. In fact, I couldn't recognize it. On the left-hand side is from our LiDAR system. That's really, I took the snapshot at 11 p.m. So there's some traffic light, but overall, the whole quality is the same as 11 a.m. Also, LiDAR sensor does not have a privacy issue because the privacy concern, it seems like is being raised at the national level. So here's the architecture. As I said, we install the directional LiDAR sensor at intersections. We install 4 like cameras. So all the LiDAR sensors raw data will send back into the LiDAR hub. The hub has the perception software, so they can recognize the vehicles and pedestrians, etc. So our algorithm is connected real-time signal control status with those pedestrian information, then generate to study the pedestrian behavior, like how long a pedestrian wait, and what's the perception reaction time when they see the walk sign start, or what's the pedestrian walk crossing time, etc. And also we have ongoing efforts trying to integrate the pedestrian information into ATS NPM, which is short for Arterial Traffic Signal Performance Monitoring System. So and now I turn to Suresh again to explain the study, the preliminary findings briefly. Okay.
Thanks, Taylor. Okay, so this LiDAR system that Taylor just talked about was set up at 2 different intersections in Texas. One was at UTA Boulevard and South Cooper Street in the city of Arlington. So this is right in the heart of UTA's campus. And the second intersection was Beltline Road and Walnut Hill Lane in the city of Irving. as you can see, both these intersections had were equipped with pedestrian push buttons, so had 4 pedestrian faces at each of the intersections. The only difference being that at the intersection of UTA Boulevard and South Cooper Street, the pedestrian push button was ADA compliant, and it had the APS signal, so it provided an auditory cue for pedestrians that were waiting. Okay. Next slide, please. The collected data over a few months for both the systems, and once the data was received, we undertook some data cleaning and to just remove the records that had incomplete information. So, for example, zones were drawn for the system, and if a pedestrian, for example, stepped off the zone before they finished their crossing, then the complete information for that pedestrian was not recorded. And so such observations were kind of removed before these preliminary analyses were conducted. And so at the Cooper Street and UTA Boulevard intersection, we collected data for over 2,500 pedestrians, and the average delays there, as you can see, were sort of higher as you would expect for the minor street faces, that's 4 and 8, and lower for the main street faces. Overall average delay was about 49 seconds. The average perception reaction time was 2.1 seconds. And again, thing to note here is this is an intersection that was equipped with the APS device. And even with that, the perception reaction time that we are recording is more, 1 second more than the average value that is being used in the literature currently. And the average crossing time was close to 16 seconds. Next slide, please. We undertook a similar test again at Walnut Hill Lane and Beltline Road, and again over 1,600 observations here. About 40 seconds was the average delay that was recorded, and the perception reaction time was significantly higher at this intersection compared to the previous intersection. And we think it's again because of the lack of that auditory clue. So people are just distracted and taking longer to notice that the walk sign has been displayed for them and to begin their crossing. And so that has implications for operations and safety at the intersection. And the average crossing time was about 19 seconds. Next slide, please. So in terms of preliminary findings, we found that the Lidar sensor was able to track and detect pedestrians effectively. And we were able to, with the use of some custom algorithms and logic, measure the average delay crossing time and the PRT for each crossing pedestrian. And based on these real field observations, we think these could be also helpful in revisiting some of these thresholds that we've been using for a long time. And again, the intersections equipped with the accessible pedestrian signals provided the auditory cues, which were helpful to inform all pedestrians about the walk time being displayed, and therefore that resulted in lower average PRT times compared to the other intersection. And with that, Taylor, do you want to wrap it up?
Yeah, let's try to give a quick demo. So I try to make the only, so here's our development environment. In fact, you see here is the live stream. So it's a ground truth. And also we have a web interface. We also have a real-time traffic signal status. So this kind of reported the pedestrian information out of our development. So So this is provided by City of Irving. In fact, they generously provide a production server for us to do this development. In fact, without their support, I don't think I go that far, because it's very difficult to build things in a live environment. And here's some future work. Let me, because we finished this part. Now we're moving on to the third step and fourth step. So how to do some real-time control, like a dynamic flash yellow arrow. And also we are integrating with other physical system, like if a pedestrian crossing intersection, so we probably get a temporary supplemental light for that. So a little longer than 20 minutes, but I will leave a question to the end. Thank you.
Okay, thank you very much. That was very interesting. So now I will introduce our third speaker, Dr. Feng. Dr. Feng is an assistant professor in the Department of Industrial and Manufacturing Systems Engineering at the University of Michigan, Dearborn. Dr. Feng's research focuses on advancing safety of environmentally sustainable, healthy, and equitable modes of transportation, such as cycling, walking, and public transit, through the development of data-driven insights, strategies, and technologies. So, Dr. Feng, I will turn it over to you now.
All right, thank you for the introduction. Let me share my screen here. Can you all see my screen, maybe in a few seconds?
Yes, we can see your screen.
Okay, first, thanks Tran-SET for inviting me for giving this research talk. It's my pleasure to share with you guys some of the recent research project that we did. So first, I want to spend just 1 or 2 minutes talk about some of the general research that we do in our research lab. So this is our research website. It's fangroup.org. Later, I'm gonna add this URL to the chat message. Actually, I'll do that in just a moment. So if you want to know more about our research, feel free to check out our website. So basically, we do a lot of work related to advancing the safety of cycling and walking. So if you look at this picture here, this is one of our recent projects where also kind of related to the previous project that we're using LiDAR mounted on the bicycle to record the riding information and the interactions between drivers and the cyclist. So this is a recent work we just started. Here it shows the point cloud data where in this particular case, the vehicle was trying to overtake the bicyclist. So we have the point cloud data recorded that we can use for measuring the accurate distance information between the car and the bicycle. And also, so this is a project I'm going to talk about here for the naturalistic cycling study. So we put the cameras and other sensors onto bicycles and record people's everyday cycling trips. And then we also recently developed a virtual reality cycling simulator. As you can see, you can kind of simulate different driving and cycling scenarios. In this case, a particular dangerous cycling experience where a car passes the cyclist very closely, close pass. So we can safely simulate this kind of experience on a VR cycling simulator from the cyclist perspective. So we also do research on using the naturalistic driving data. So we have previous project where we have cameras and sensors on vehicles, and then we can record the interactions between driver and cyclist and pedestrian from the driver's perspective. So in this particular previous work, we analyzed how much the vehicle driver move over when they pass the bicyclist, and we can analyze their passing behavior, the depending on the vehicle, the road infrastructures, for example, the lane marking types, and also the traffic conditions. So these are kind of the research work that we do in our lab. And also a plug here, I'm looking for PhD students next fall. So if you know some students who are interested, please feel free to let them check out our website if they're interested. So for this particular talk, I want to share one of our previous project we just finished that are related to naturalistic cycling study. We did in Ann Arbor, Michigan. So here's my email address. If you want to ask me any questions or looking for collaborations, feel free to drop me an email. Again, this is our research group website, fangroup.org, if you want to know more about our research. So for this particular naturalistic cycling study, we are trying to collect continuous high resolution and quantitative data of people riding bicycles in their everyday trips. So here is our instrumented research bicycle. As you can see here, we're using an electric bicycle. It's a Gen Z brand. And then we mounted a number of cameras, one camera facing forward, one camera facing the rider, and two cameras facing the left and right rear. And then we're using a GoPro, so they have a pretty wide field of view. So it kind of covers close to 360 degree of the riding environment. And also we have the GPS signal that we know exactly where they're riding. And also we have onboard data acquisition system. So everything is enclosed in this 3D printed box here, so that if it's raining or some bad weather, it can, oftentimes the rider would park the bike outside, so that would not affect our system. So, and also on the handlebar, we have the event marker. So the idea is that we kind of want to also collect the data about people's subjective perception of riding safety, even though there's no crash, but sometimes just because it was a dangerous encounter, the rider may not feel very safe. So they can always push that button to let us know. So whenever the rider push the event marker, that gonna later we as a researcher can go back to the exact moment to check what actually happened. So that's our research bicycle. And here just a close-up view of the front cockpit. So we have the event marker here, and we have the rider cameras. So this is a field of view. So we have the forward view, rider view, and the right and the left rear view, as you can see here. And also we developed software that allowed us to kind of synchronize all the data channels, including the 4 camera channels, as well as some other channels, for example, the riding speed, whether they're using the brake or not. And also we have the IMU, the accelerometer as well. And also that is linked to a Google map, see the satellite map. So we can easily review all the data together in this software. And then this is just a collection of the list of the data channels that we're collecting. So we have 4 video channels and audio channels, and we're using GoPros, and we have the GPS signal, which is fairly high accuracy. The accuracy is about 2 meters, and they're collected at 20 hertz. And it gives us information about where exactly they're riding. So here it's just some of the aggregation of the GPS data points at the intersections in Ann Arbor, Michigan. You can see where actually people, whether actually they're riding on the road or on the sidewalk. So our GPS actually have the resolutions for differentiating that. And also we have the IMU as well as some other data channels as well. So when we designed this research bicycle for this study, our idea is we want to record people's natural riding behavior. So we actually we give the bicycle to participants for 2 weeks. So they actually gonna bring the bike home for 2 weeks and ride the bicycle as a substitute for their personal bicycle. So we really wanna make sure that the data recording is always working, and also they're not gonna break the bike. So we follow this KISS principle, keep it simple, stupid. So we actually spend quite some engineering time just to make sure everything's robust and working. So, and also they are small size, that they're not going to affect too much of their bike handling. And also they need to be weatherproofed. And also, this is one of the idea that we actually used the electric bike, because we actually draw power directly from the e-bike battery, so that we don't really need to add another secondary battery just to power the DAS and the sensors. So because the rider also needed to charge the electric bike battery anyway, so there's just not that extra step that they need to remember to charge our data acquisition system. And also we design the software so that it's automatic recording. So whenever the bike is in motion, measured by the wheeled speed sensor, it's gonna automatically start recording, and whenever the bike is stopped for more than a minute, then the system gonna enter the sleep mode. So the whole idea is that we want to make it really easy for the rider, so that they don't really need to remember any additional steps, so they just ride the bike. So our data collection was actually for 2 years, 2 riding seasons, 2018 and 2019, in summers and fall. And we're actually we're lucky that we actually just finished our data collection a few months before COVID started, when we cannot really collect any additional data. And the subject were mainly already bicycle riders in the Ann Arbor area. And we give the bike to each of the subject for 2 weeks. And then at the end of the study, they will come back to our lab, and then we're gonna just download all the data. And then over the 2 years, we collected 77 subjects, and then that's a total of just over 8,000 kilometers, or about just over 5,000 miles of riding data, and over 300 hours of riding. So this is what the visualization we did. The GPS data, we can actually aggregate all the GPS data points from all the riders, and we can create this kind of heat map. So this one is generated by, you believe it's probably over 10 million GPS data points. If you're familiar with Ann Arbor, this heat map basically shows almost all the major streets in Ann Arbor. So in the middle is a downtown area, and then we have some major corridors. As you can see here, basically people are pretty much riding everywhere. And there are certain roads, even though it may be a major road, but because there's lack of bicycle facility, so this is Washington Avenue, which is doesn't have a lot of bicycle facility, even though it have a lot of vehicle traffic, but not a lot of riders were on that particular road. And we can also kind of zoom into the heat map to see at a more local level where people are riding. So this the one on the left is some of the downtown area, and then on the right is just one of the intersections where we can see where exactly people are riding by looking at the GPS heat map. And then here is just one of the video clip that recording one of the scenarios where the rider pressed that event marker. Here's a video I can just view. I apologize, because of the internet connection, the video may not look very smooth. But this is just one scenario where it's a right hook. The white car in front at the intersection was trying to make a right turn where it's kind of cutting in front of the cyclist, which is trying to go straight. So this is just one of the what we call the safety critical events that we recorded. So this is another example where it's a close pass. So basically the car from behind was passing our study participant very closely. You may see that in the video. So we collected all these danger scenarios from our data for the analysis. And also we have some aggregation of the some of the riding information. For example, we can check their average riding speed, which is actually not very high. Average speed is only about 20 kilometers per hour. And also we can check the riding time of the day. And quite a number of our study participants was using the bicycle for commuting purposes. As you can see, there's a morning peak, and generally the largest peak is in the afternoon when more people are riding more. And also we can look at the riding distribution of the trip distance as well as the trip time. These kind of summary statistics. And then we also look at the what we call the safety critical events, where the rider, either the rider recorded the press that event marker button, or we basically reviewed the videos to determine that is a safety critical event, and we can kind of classify those into different types for further analysis. So for the sake of time, I'm not going to talk more about this table. So here also at the end of the 2 weeks, we also have a short survey for the riders to just kind of get some feedback about their experience of using the e-bike. So the large majority of the participants very positive experience using our e-bike. So some people mentioned it's easier for going up hills, or it's actually easier to stop at the stop signs just because it's easier to re-accelerate from zero on the e-bike. And also they can get through intersections faster, and they don't sweat once they get to work when they may not have a place to take a shower. And then also it's just simply easier, remove the mental block of too much effort to riding a regular bike without the power assist. And also this is one I found really interesting. Some participant mentioned that I stopped looking for the absolute shortest, the flattest route, and went for a more pleasant one. So using the e-bike also people to make this kind of route planning decisions so that they can find one, even though it's a little bit longer or hillier, but maybe that's a lighter in traffic, so that they can ride with the same amount of effort. So we have a lot of these positive feedbacks, and so that's. I want to briefly talk about this work, and we are submitting this the conclusion about this to a journal article, which I hope gonna be published soon. So that's all I have, and I want to acknowledge my co-PI, Dr. Shan Bao, as well as the sponsor for this project, Toyota Research Institute, as well as my collaborator at the University of Michigan Transportation Research Institute. That's all I have. Last slide is my contact information. If you are interested, feel free to email me. And also this is our website. Thank you.
Perfect. Thank you very much, Dr. Feng. So this concludes the presentation portion of our webinar. Now we'll be receiving questions from the attendees. So if you have any questions, feel free to type it in the chat box, or you can unmute yourself and ask the question lively. So right now I cannot see any questions. So just a reminder that next week we will have the recording of this webinar uploaded on our YouTube channel as well on our website. So again, if you have any questions, you can reach out to the presenters.
So if no question from audience, if I actually have a question for Dr. Fan. Okay, so very interesting presentation. Of course, everybody else also has a good presentation. So I have a question regarding the GPS sampling frequency. they use a 20 hertz, but the GPS, as far as I know, is a kind of 1 second update. So what's the 20 hertz used for? Is that combined with other sensors, like a motion sensor, things like that?
So most of the, if you use any, the common GPS, it's a sampling rate of a 1 second or 1 hertz. So the one we got is actually one of the, for a GPS sensor that is actually integrated with IMU. It's an integrated unit, actually records at 20 hertz. So is your question about whether that's needed?
No, I'm not asking if it needed, just if it is updated enough, because the GPS from satellite is a second by second update about coordinates. So, but of course, if the integration with other sensors, maybe other sensor has a much higher frequency, like a acceleration, that makes sense. Okay.
Yeah.
Okay. Thank you.
And also, typically the riding for our application, the riding speed, most of the people would ride, let's say, slower than 30 miles per hour. So that's a relatively lower speed compared with, say, vehicles. So the sampling rate it's good enough for capturing their cycling trip.
Okay, thank you.
Okay, so I can see a question in the chat box to Dr. Feng. So the question is, why didn't you track the riding habits of cyclists in the winter?
Actually, great question. So at the beginning of the study, we are having some concerns that we're not going to get enough riders that are willing to participate in the winter, because the winter in Michigan is pretty cold. But we actually indeed found some people, they just commute all year, or they just don't mind to use that. And we actually had a number of subjects participating in our study in December, which the temperature was pretty cold. But the problem, this is one of the limitations of an e-bike that we used, which is the battery basically does not hold charge when people park the bike outside for work for hours in the winter time. So we actually got a number of calls from the rider, basically after work, the battery entirely, there's no charge left. So that is one of the things. We have limited data in the winter, so we have to call it a day for that December data collection, simply because the range of the battery just get not enough in a lower temperature. I would say typically under 30 degrees Fahrenheit, which is typical in December in Michigan. It's too low for running this study. But if you're in a warmer area, like in Florida or in the southern area, that may not be an issue. Yeah, but we would love to maybe collect some data elsewhere when people are riding all year long. Thank you.
Okay, thank you.
Excuse me.
Answer. So I think we have for us, do you have a question?
Yes.
Okay, yeah, you can
Do you
go.
hear me?
Yeah, we can hear you. You can go.
You distribute the biking for to study some research. My question is about your samples of people when you distribute this biking. Do you think there are a different data? You will collect a different data for the people who now who are they drive biking for collecting data, or those people who don't know who they drive the biking for collecting data? Do you think they are different? They do a different behavior when they drive those bikes?
I guess is that question for me, for my study?
Yes, it's for you.
Oh, okay. So yeah, we certainly had some. We have the pre-screening process when we selected those riders. some of the major criterions are we want to make sure those are the people who are already riding a bike regularly. We don't want to put someone who never ride a bike before to participate in our study. And also there's some there's some other practical constraints that we have to meet. For example, because the research bike is it's a very valuable, and it's very heavy. We actually looking for people who actually can guarantee that they can park the bike inside at night rather than, so that actually excluded a lot of students who are living in a dorm, so they don't have the space in their dormitory, things like that. So I would say our study the result basically is not a representation of the general population, which has a wider range in terms of their driving and cycling experience. But it's really sampled from those people who are already in using cycling as part of their daily activity.
I don't know if you get my question correct or no.
I'm sorry. So what can you?
Yeah. I mean, when you distribute the bike for people,
yeah.
Do you think the people they behave the same when they ride a usual daily biking?
That's
or maybe
they
behave different when?
Yeah, that's always one of the limitations for this kind of study. One thing is it's a fair question that when they are riding our bike, they may behave differently than they would on their own bike. So they may think that we are kind of evaluating them as a rider, so they may behave in a certain way than they would normally ride. So in our study, we did in our instruction, when they are picking up the bike, we have a list of instructions to ask them actually to ride in a safely manner. We don't really know how well they ride before, but we ask them to. There's some baseline. You have to obey all the traffic laws. You have to wear a helmet. You have to have the lights on. You have to. It's just some of the things also guided by the IRB process. So it's possible that they may behave differently than what they normally would. That's one of the motivation we have our study for 2 weeks rather than a couple of hours where people may not even care. So our rationale is if it's a longer period of data collection, people may hopefully kind of just our data is reflecting their more of a normal riding behavior.
Okay, thank you very much. So I would like to thank our 4 presenters for their time and technical presentations. I would like also to thank all of our attendees. Please let me know if you have any other questions about the webinar series or about Tran-SET in general. Otherwise, have a great rest of your day.
Thank you.
Thank you.